Hi everyone, welcome back to my video series on artificial intelligence. This is part 1, section 3, or explain-02. Please note we're counting up from 0. The URL with the Jupyter notebooks is here. Okay, so let's get started. In prior sections, we covered the basics of calculus, matrices, vectors, tensors, and the common operations on them. Matrix multiply, matrix times vector, dot product, matrix transpose, or vector transpose. We also introduced activation functions, which is the amazing key invention that we owe the existence of artificial intelligence to. Now we're going to cover the second important invention, this time in software hardware, which when combined with GPUs allows anyone and everyone to create and train their own AI engines. This, of course, is called backpropagation. But first, I'm going to talk about a motivating example of an image classification problem. So let's assume that you have a set of tiny images, say tiny ones, 25 by 20 or so. These are small. And let's assume that the images are split into 10 different categories. So in this case, you want to train your neural network so that your network can recognize which category your each image is in. So in this case, because the images are say 25 by 20, the neural network has to take in 500 inputs. And let's say if the images are has 10 categories, let's say shirts, shoes, handbags, so on and so forth, then it has 10 outputs, right? And what you do is you feed in each pixel value of the image to a corresponding row of the matrix. And then the key idea here is that you want the neural network to output a 1.0 in exactly one of the outputs, depending on which category the image belongs to. And for this, we can use hyperbolic tangent, tanh, as an activation function. Why? Because it clamps the inputs down from whatever it is down to between -1 and 1. So what you do here is you create a matrix, say 10 by 500, and fill it with random values between 0 and 1. Sometimes -1 to 1 works too. And this is one of the hints as to why even though the math is simple, the problem of AI can be difficult. It's because choosing the right design of your neural network can be difficult. Okay, and some formulas only work for certain problems, meaning there is no generic formula for designing a neural network. Okay, getting back to the motivating example, what you do is for each image, simply do the tanh of matrix times vector. Now here in this case, you have to remember the vector is 500 has 500 values in it, or 500 numbers, and each of the numbers in the vector is basically the corresponding pixel value from the image, and then you just see what you get. Now what you can do is you can create what's known as a loss function. So why do we need to do this? In order for you to figure out how far your newly birthed neural network is from the meaning how useful it is, you need to figure out from the it's going to spit out something. You feed the neural network an input, say an image, and it's going to produce some garbage output, okay? And you need to figure out how far is the garbage output from the output that you want. And that is the loss function. Okay, so in other words, you can calculate how far off the answer that you want, right, from the answer that you actually get. And then what you do is you sum that error value up for each test image, and that is the loss. So are we done? Do we just plug in the matrix times vector into, say, a symbolic math package? Remember, we use I showed you SymPy, right? Into symbolic math package and just have it calculate the differentiation, right? And no, it's obviously not going to be the right approach. And let me just demonstrate why. Okay, so I'm just showing you that look at that SymPy does lots of cool stuff like Wolfram Alpha does. Right, here's something a little more complicated, right? Right, and so by the way, SymPy does have matrix stuff in it. Okay, so for example, we can do stuff like this. Okay, now what we want to do is here's a very simple neural network. It just has three by three, and the input just is a 3-element vector, the input y, right? And then now we want to ask the SymPy to differentiate it with respect to a. Okay. And it's really not going to give you anything very useful. Let's see. Let's try this one. Okay. Whoops. Huh. Interesting. Right? So trust me on this one. The plugging the matrix times vector into a symbolic computation package and asking it to give you the solution is not going to work. It's just not going to work. Right? And this is another bizarre little trick. Right? And if you understand how chain rules actually work, you already kind of sort of already know what this trick is, right? And it turns out that you can calculate if you have a complex expression, let's say a matrix times vector or a matrix times matrix times matrix times a vector, so on and so forth, with an activation function somewhere, what you can do is you can do a piecewise derivative. You can calculate the gradient, in other words, right? Piecewise. And what you do is using the chain rule, you sort of chain it backward towards the input variables, and you're done. So, right? And that's literally the invention. Right? And it really didn't take off. I mean, people knew about this, obviously, because the chain rule, it's pretty obvious once you think about it, right? How you might calculate the piecewise derivative of a complex equation. And but the issue here is that it really was not of use until we had GPUs, and then it still wasn't much of use until people started to code up systems like TensorFlow and PyTorch. Okay, so it really needed, all of these things needed to be in existence for the AI boom to actually start. All right, so let's just get back to the history, or the general methodology. So if you have defined a good loss function, right? You have the output of the loss function, which is going to be some number, and you want to figure out how to change the values in the matrix so that your resulting loss is minimized. In other words, loss rate. This is why when you see most loss functions and graphs thereof, the loss is generally configured as a number that is greater than or equal to 0, right? Because you want the loss to be minimized, and it probably doesn't make sense for the loss to be negative, right? It probably doesn't make sense. So you want loss is a number that you calculate that goes from 0 through whatever, right? And the key secret here is that first you start off with the idea that derivative of anything respect to itself is 1, always. Okay, so now you generated the loss values. Just forget about the complexities of an actual neural network. Let's assume that you somehow arrived at the final value of the loss, right? So meaning the loss is some scalar value that is usually going to be greater than or equal to 0, right? And then feeding into the loss is some very, very complicated mathematical expression that sort of ends in the inputs and in the middle has some matrices, okay, that are randomly initialized. The matrices are randomly initialized somehow. Okay, so now what you can do is you calculate d loss respect to the next stage. So what is the next stage? The next stage is basically the linearized or the sequence of sub-expressions in your complex neural network. Okay, so for example, let's go over here. Right, so let's assume that this is your neural network, right? X is the matrix and V is the input, and you have some bias, B. Okay, so you say y equals tanh of matrix multiply of x times v, v being your input, plus some bias. Okay, and the loss you say is, you know, for given the input, you know what the answer is, so you subtract it from the output that you get, and then you square it. Okay, this is known as the mean squared error loss. Okay, so this loss is the final expression in your neural network while you're training. And y is the next stage. Y is basically tan h of something. The next stage is add bias to v1, and v1 is the matrix x multiplied by v. Okay. In this case, only the matrix x and the bias vector v are the parameters of your neural network, and v is the input, right? So what are we doing? We want to figure out how to change x and b so that you minimize the loss with respect to the training set. So what is the training set? Training sets are the inputs, the individual v's, right? And also the expected outputs, the y answer. That is the training set. Okay? So how do you calculate the derivative of a matrix? It's simple but annoying, and we'll cover it later. Remember that what we want to do is we want to calculate the new the grad field, right? So basically, remember we started with a value class. We're going to be adding another thing called dot grad or dot gradient. Okay, so we need to calculate the outgoing gradient with respect to each left hand. So for example, if the operation is a matrix times a matrix, right? So you need to calculate the outgoing gradient with respect to each I sub j of the left hand, and the same for the right hand side. Okay, so for example, if A is shape 3-4 and B is of shape 4-2, and then if some intermediate stage we have a matrix multiply of A by B, the result is going to be a 3x2 matrix. Okay, so what you do is now you want to calculate the partial derivative of your loss, which is somewhere out here over to the left, with respect to A, right? But that takes multiple steps. But what we have instead is basically when we get to this part, C, right? We're going to have C's gradient, and then we're going to somehow generate the gradients for A and B, right? Because we have the output value C, and then when we get to here in the backward stage, we're going to have C's gradient, and then from C and C's gradient, we have the values A and B, right? Because we just use that to generate C, right? So using A, B, and C dot grad, we're going to be generating A dot grad and B dot grad. Okay. Now, all of this, this probably just flew over your head, but we'll cover that next. Okay. Thank you very much. This is the end of part 2. It was again very, very, very short and sweet. So so the next video we're actually going to jump into some more Python code. Okay. Thank you very much, and see you soon.